So today we're looking at software-defined networking, and in particular the OpenFlow technology. You've got a recording of this already from Richard Mortier. What I'd like to do though is dig into a bit of the details about how you'd use it, how you would actually code this stuff, because for me one of the fascinating things about it is you can write your own switch software. You can write the brains of a router or a switch. And that's, for me, one of the big interesting things about it. And the other thing is, you could get a bunch of software switches running the OpenFlow protocol going just on a humble laptop. You can sort of build your own data center. You can have hundreds of switches connecting to each other and write a controller. For the full details, you should watch that's an excellent video already on your channel. But I just want to recap about the sort of thing we're dealing with. So key for me in understanding this is separating what we call the data plane and the control plane. So let's imagine we have some bunch of switches sending data about. Now switches are often pretty simple-minded in what a normal switch can do. So they're connected up in a topology. Now, normally you just configure them, they go away and do their thing. Maybe we want a little bit more cleverer control. If we've got these OpenFlow switches, we can add on top of them the OpenFlow controller. So it's a software component that speaks to a software component in these switches. So if you imagine each of these switches, there's a little software component in them, and they can speak to a controller up here. Now, if you think about what a switch does, it's got two tasks. It's got to move the data about, so it's got to take packets in, and it's got to push those packets out, decide whether it wants to keep them or drop them, and then move those packets out and decide which of its ports it wants to move the packets out. So maybe it knows that the data's got to get to here, so it's going to move the packets down here, move the packets down here, move the packets down here. Now, moving the packets, that's the job of the data plane. When I think about the data plane, I think of it as being very much a manual laborer. It's looking at a simple set of rules, and it's saying this packet is going to this particular Ethernet address, so it needs to go left. Picks up the packet, moves the packet, done. This particular packet, that's not from a trusted source, we're just going to drop it. This particular packet, we're going to send it out, we're going to flood it out to all of the switches that I know, so I'll send it out to everyone. And it's got a simple set of rules it works with. That's the data plane. The question is, where does that set of rules come from? Now, normal switches have various algorithms they work with, but in an OpenFlow situation, you have the ability to write your own rules and to react to unexpected events. So in the OpenFlow situation, a packet comes in, the switch looks at its list of rules, and if the packet doesn't match any, it's going to send up a little query. It's called a packet in event, and it's going to say, hey, controller, just got this packet. I don't know what to do with it. The controller will look at its software rules. So it's software you can write in a standard language like Python, and it will say what to do with that particular type of packet. And then you come up with a rule. So you say any packet going to that particular Ethernet port, or any packet from that subnetwork, you're going to follow this. And it replies to the switch with a new rule to meet what's happening with that packet, and now the switch knows what to do with that packet and all packets that are like that one. Yeah? So we've got a situation where the controller can responsively see a packet where it doesn't know a rule and give the switch a new rule.
So it's a bit more dynamic rather than being kind of like hard-coded or hardwired. It can be a bit more fluid.
Absolutely. And the great thing is this can work for switches and routers. So if your topology is more complex than this, and there's actual routing at the internet protocol layer going on, the OpenFlow controller can work with that as well. We've talked previously about Bowman-Ford or Dijkstra algorithm with routing, but those always just work on a destination. Now let's imagine you have something more complex. So you think, I've got video traffic, which takes up a load of bandwidth, but I've got my gaming traffic. It's got to be quick, but it doesn't take a lot of bandwidth. Maybe you can devote one part of your network to being fast and low latency, and another part of your network to being a little bit slower, but it's got a lot of bandwidth. So you could send your video traffic one way, your gaming traffic another way. And you can add in lots of other things. So you could add in a firewall. So that switch can say, this location, I trust, all of the traffic can come through. This location, they can only see the web server, nothing else available to them. This location tried to hack me last week, and everything from there is going in the bin.
Something like this, it might be literally my house where my son's trying to play Fortnite or whatever, so he needs the fast traffic, and every time I hear this knock on the door saying, "Daddy, are you uploading a video?" maybe it would make that go away, would it?
If you had multiple paths in your house, if your house had a network with multiple paths, you could say, okay, mine's going to go on the slower path, his is going to get the priority there.
I might switch that round, but anyway, carry on.
Oh yeah, it's true, actually. It depends what you want. Yeah, he shouldn't be playing Fortnite. Got him with his schoolwork.
Absolutely.
So we've got there this separation now with the OpenFlow system into the data plane, which is just obeying the rules, and the OpenFlow system, which is the controller, which is setting the rules and receiving these packet in events, these exceptions to the rules. One of the things that's just very easy to play about with is a tool called Mininet. And I love it. It's just a gorgeous bit of software. And its job is to create software switches and software hosts. Yeah? So we can set it up in a really, really simple way. And we can just do the absolute basics and see it working with some simple commands. So, okay, so let's start it up. Just in a real simple topology, we've got two hosts and a switch. And we can see here it's added in some links between host 1 and switch 1, host 2 and switch 1. So now we've got a really, really simple topology, host, connected by switch. And now we can issue commands as if they'd been issued from a particular host. So we can say h1, ping h2. And what that means in Mininet's language is host 1, send out a ping packet to h2. Not very spectacular, but that's using the proper networking code. This isn't an emulation. This is the real ping command, sending real packets through a real software switch. It's not that exciting. So let's do something a bit more interesting. So within Mininet, we can build up our own topology. So we can actually write in Python the network that we want to produce. It is a super simple topology, but here's our Computerphile topology written in Python. We've imported some commands from Mininet, and all this says is we're going to add a host, h1, and we'll assign it to the variable left host. We're going to add a host h2, and we'll assign it to the variable right host. So this is setting up some Python objects, left host, right host, and adding them into Mininet as host h1, host h2, switch s1, and switch s2. And now we can add some links, add a link from the left host to the left switch, add a link from the left switch to the right switch, add a link from the right switch to the right host. So we've got just a simple line topology, but we could make that as complicated as we like. And we could do it programmatically. So we could use a for loop to make that line as long as we wanted. And then there's just a simple command here to start off the topology. And let me just demonstrate how that starts. So I need to stop Mininet, and I'm just going to do a little clear up to make sure that all of the software switches it started have gone away. Otherwise there'll be problems. And now we can start our custom topology. There we go. And that has obeyed the code I've put in here. We can do exactly what we did before, h1 ping h2, and we're sending packets through.
Just to be clear, so this isn't simulating, this is literally doing this but via kind of virtual machines almost, is it?
Yeah. Virtual switches. It's setting up virtual switches, routing those, switching those packets, and genuinely delivering packets. So it's not a simulation. It's genuinely sending those packets.
Mm-hmm.
Now, what we can do with this that ties into the OpenFlow is we can ask that those switches are OpenFlow switches. That means, though, that's not going to work unless we have an OpenFlow controller. We've cleaned up our controller, and now we're going to start again, but we're going to this time say, instead of using a standard switch, we're going to use an OpenFlow virtual switch running the kernel. So switch OVSK is an OpenFlow virtual switch running in the Linux kernel. But when I start that off, we have a problem because we don't have a controller. So I start it off and it's going to say, come back there, could not find a default controller. Like I said, the data plane is the manual laborer, the controller, that's the brains, that's the person creating the rules. And if we start it like that without a controller, it's going to complain. What we need now is to start up a controller. So I'm going to use a very, very simple demo one. This is demo code that comes with the POX Python controller. The job of this controller is to catch those packet in events and provide rules when it gets a packet in event. Yeah? So it's connecting to all of our virtual OpenFlow switches and listening for those switches saying, oh, I've got a packet and I don't know what to do with it. And this is the software that catches that and decides on what rule goes with it. Here, it's just doing some housekeeping. This is from somebody else's tutorial code, by the way. I should say I did not write this code myself. Handle packet in. So this is the heart of it. We're going to get a packet in. So this is an event that happens on the controller when a packet doesn't match any of the rules on the switch. So here, we've got this packet in event. This line is just parsing it and switching it into the correct OpenFlow term. And what we're going to do here, we're going to say act like a hub. So just send it out to everybody. Just a hub. A hub's very, very simple. If I don't know what to do, I'm just going to send that packet on to everybody. I'm going to flood it out there. So we need the act like hub code. And this just says resend the packet. So take my packet in, resend it, and send it to everybody. Yeah? So the packet's just going to flood out. Everybody's going to get it. And it's fine. That absolutely works on this type of switch network. So just that simple logic is going to be enough to get our controller working. So I've started up that tutorial code, and now I'll just do a cleanup on the mininet, and I'll start up the mininet --controller remote. And that's going to tell it you have got a controller, it's running on the same computer, and there we go. And we can see that this has started the topology we programmed, and this is parsing some of the things. Now we can do our H1 ping H2, and the data's getting through. Okay, so you might say, sort of prove it to me, is this really going through the software? So I could say packets is 0. So set a local variable to keep track of the packets in the class. And then when we are acting like a hub, self packets is self.packets +1, print counted packets self.packets. And now start up the controller, reset mininet. So I'll start up mininet with my custom topology, and now it's counting the packets. I'm still throwing some DNS errors, and I'm not quite sure why. I don't know why it's getting DNS packets, but you can see it's counting the packets as they come through. This is still falling far short of my promise that it can seem like a data center, right? Still seeming pretty basic. But we can make more complex topologies. Now to do this, I'm going to step up and I'm going to use a different controller. So I'm going to use here the floodlight controller. So this is a large bit of software. It's getting a bit old now in terms of these OpenFlow controllers, so you wouldn't use this in a production network, but it's very nice just as a demo bit of software and to demonstrate to your viewers how we can get a group of switches working on OpenFlow. The nice thing about the floodlight controller is it's got a web interface. If I browse to this web page on 127001, my own computer, we can see that it's active. It's been running for 27 seconds and it sees no switches and it sees no hosts. Let's start up a mini-net topology and let's make it a tree topology. So we're going to run a more complex topology. So my command here has started a topology for a tree with a depth of 3, a fan out of 2, connected to the remote controller using OpenFlow virtual switches and the version 1.3 OpenFlow protocol. With this we can see that the OpenFlow controller is seeing 7 switches, 19 hosts, 12 connections, and we can see a topology wired up. So we can see that this topology reflects the tree that we've set up. And we can be more ambitious than that. So I can set a slightly deeper tree, have that connect to the controller, and hopefully the topology will reflect the increased complexity. We've just set it so it's got a few more switches. And I can push this quite a long way. So let's say we want to be just a little bit more ambitious. Let's set those tree parameters a bit more. So get more towards what I promised, which was you can have something a little bit like a data center in our laptops. So I'm going to try the tree with a depth of 4, a fan out of 3, but otherwise the same things. The remote controller, the floodlight controller we were using before. So now it's starting up all of those hosts, it's starting up all of those switches. We've got 81 hosts, 40 switches, wired up in a tree. I can say ping all, and this will send ping packets between all of those hosts. So here, H1's pinging everything, and now if we go over to our topology and refresh that, hopefully this should start to catch up and it should work out that we've got a tree topology. It can take a little while when there's so much data going through. So it just take a little bit of a while to absorb all of the topology information it's getting. And there, we can see quite nicely. Can I zoom in? Look at that. I think that's absolutely lovely, to be honest. I find that quite exciting. And just to emphasize again, this isn't a simulation. In a simulation, this would be very, very easy. But this is actual packets being routed. So if I say that's H48, and if I say H48, ping H5, it's going to send genuine ping packets down that topology.
Can we use Traceroute through it?
We can use Traceroute, but these are all switches. And Traceroute only looks at routers. So Traceroute will always be very, very simple in this because it's only one hop. None of these count as part of the route. If we had a layer 2, a switch-based Traceroute, then we could see something real interesting with that. But unfortunately, we don't.
Well, it definitely looks like the data center's taking shape there on that web browser.
For somebody like me as a researcher, this is really exciting because let's imagine I have some new research idea for how switches should work. And I want to experiment with that. In the old days, where switches were just didn't have this OpenFlow capability, what I would have to do is persuade somebody. I could try it out, I could simulate it, but I would then have to persuade somebody to build a switch using silicon, tremendously expensive. And then I go, oh, you know what? My algorithm needs a bit of a tweak. Could you build me another one that does this? Here, I can experiment just on my laptop. I can write new things into the controller. I can write new algorithms, new ways of doing things, try them out, see how it goes in these software switches, and then buy OpenFlow switches. They're just a commodity product. You can just say, buy me 40 OpenFlow switches. They're already there. And I can test my new OpenFlow controller in a real network, having tested it on software switches within my laptop. So it's just a tremendously exciting way to play about and learn about how these OpenFlow switches are controlled and how you could control them in a real network.
Standard Computerphile question now, though. This is all open source, I'm guessing. People can go and play with this now, could they?
Yeah, absolutely. I'm going to put things on GitHub, so hopefully people could build this software, play with it on their own machines. So if you've got Linux, if you've got Ubuntu, you can just installing Mininet. It's just a single command, and you can just play about with it.
Cool.
Have fun.
Cool.
Learn about it.
Or make nice, pretty snowflake pictures with your topology.
Yeah. Or just enjoy the fact that we've got a lovely fractal snowflake-like topology. In 2, that routing table is going to arrive with green. Green's going to say, oh, you can get to blue in 1? Brilliant. I've got a cheaper cost to blue. It's going to hear for the first
because
time.
otherwise we'll be sitting here a little bit longer. Then we've got 60 possible positions. We've got to choose 3 out of 5, and then they can all go in any